In this presentation, I'd like to share our work edge-aware 3D instance segmentation network with intelligent semantic prior. Let's start with the introduction of our paper. Understanding 3D scenes is a fundamental task within 3D computer vision. Given 3D point cloud scenes, the 3D instance segmentation task identifies individual instances and assigns corresponding semantic class labels with the goal of comprehensively understanding entire spatial 3D environments. In real-world 3D scenarios, significant occlusion and truncation often occur, especially when objects are overlapped or hidden by others. To address these issues, conventional works in 3D instance segmentation primarily focus on accurately generating region proposals or effectively grouping points with clustering algorithms. However, these methods depend on intermediate processes, such as bounding box detection or heuristic voting mechanisms, to determine specific geometric properties. Recently, transformer-based 3D-IS frameworks have tackled several limitations of traditional approaches by introducing a fully end-to-end pipeline. They directly predict masks based on attention architecture without resource-exhaustive processing. These methods have achieved high performance and quickly become predominant in the 3D-IS domain. Despite these breakthroughs, they still face challenges in accurately masking everyday 3D instances relying solely on geometrical information. Specifically, they frequently suffer from cases where each instance appears similar, but their semantic roles differ. Thus, gaining insight into the semantic properties of instances beyond mere appearance or position is crucial for effectively addressing complex real-world 3D scenarios. From this observation, in this work, we consider leveraging semantic knowledge along with the geometry information. Furthermore, we empirically observe that most 3D-IS models struggle with precisely capturing the boundaries in the 3D space. These methods often misinterpret the spatial range of instances and ambiguously determine their edges, leading to numerous misclassifications of adjacent edge points. We consider that these issues arise due to the absence of detailed guidance on inter-object boundaries, resulting in fuzzy edges. To tackle these challenges, we advocate for leveraging the Edge Prediction module to pilot the whole network to exploit edge advanced features. We predict edge points across 3D scenes and use them as auxiliary information for learning edge cues, improving segmentation accuracy. In this section, I will introduce a novel 3D instance segmentation framework leveraging rich semantic guidance and effective edge cues. I first provide an overview of our framework and then present technical details of our method. Built upon the classic architecture of the transformer-based model, our model takes 3D scenes and directly infers instance masks. Our model consists of four main modules. First is the sparse convolutional U-Net backbone, which extracts multi-resolution feature maps from the input point cloud scene. Second is the semantic network, which strengthens the queries to learn contextual variations of instances with rich semantic embeddings from the pre-trained language model clip. Then, the mask transformer decoder with mask module and query refinement blocks, which iteratively updates the instance queries using attention strategies. The last is the Edge Prediction module, where our edge extraction head predicts a voxel-wise edge map, encouraging the network to utilize edge advanced features. I will explain each module in more detail. The backbone takes a colored point cloud P as input and voxelizes P into X0 voxels to extract multi-resolution hierarchical feature maps Fi. Then in the mask transformer, we set 0 initialized non-parametric instance queries Q, referring to point positions sampled with furthest point sampling. Given the Fi and Q, the mask transformer decoder layer iteratively enhances the queries using the mask module and query refinement blocks. Specifically, in the mask module, we classify the category of each query via linear classification head F-class using cross-entropy loss. Also, the queries are fed through the query head F query to project them to the same feature space as F0 for mask prediction. Afterward, we process the dot product of the projected query feature Q' and F0. Then calculate the attention mask MATTN using the sigmoid function. Further, to refine the query representation, we leverage the query refinement block, including masked cross-attention and self-attention mechanisms. Here, we utilize MATTN as the foreground mask for the masked cross-attention layer, where queries iteratively attend to each multi-scale feature, where keys and values are linearly projected from each point feature, and queries are from Q. Subsequently, in the self-attention layer, the keys, values, and queries are all linear projections of Q from the cross-attention layer. Finally, the transformer decoder layer is recurrently applied for multiple iterations and feature scales, ultimately producing the final set of refined instance queries. Let's move to the intelligent semantic prior. It is important to highlight that precise geometric properties from 3D points significantly enhance 3D IS accuracy. While previous studies benefit from the generous geometric potential of physical information, they are still limited in perceiving intricate real-world 3D instances. Hence, we propose to utilize semantic knowledge of individual instances as smart priors, effectively addressing the challenges. Recently, visual language models have highlighted the benefits of their capability to provide general embedded knowledge from large-scale image-text multimodal data. In this work, we explicitly instruct the transformer-based network to learn contextual variations among instances by utilizing the power of the prevalent language model clip. To achieve this goal, we utilize a carefully designed semantic network. Specifically, with the refined query queue from each query refinement block, we first categorize each query following the linear classification head F class in the mask module. Given the set of category candidates, we map the category number with the corresponding text descriptions. We then concatenate instance queries with text embeddings and strengthen the basic instance queries with deep semantic clues from text embeddings using the semantic fusion network. We apply this process for each iteration of the query refinement block. Ultimately, we consider these explicitly guided queries with contextual variations as discriminative semantic priors for the practical perception of complex 3D instances. Furthermore, in real-world 3D scenarios, instances are commonly positioned in diverse arrangements without following standard rules or patterns. Especially when instances are closely adjacent or overlapping, it becomes increasingly challenging for the model to define the edges precisely. Therefore, even with significant progress in technical strategies, most conventional methods often misinterpret the spatial extent of each instance and ambiguously estimate their edges. To this end, we introduce an edge-aware framework with an edge prediction module, enabling the network to utilize edge advanced features. To optimize the edge prediction module, we first compute point-wise pseudo-edge labels for all 3D point scenes. We operate a traditional k-nearest neighbors classification algorithm based on the KD tree data structure to explore the k-nearest points. For all points, we set each point as a central point and compare their instance labels with those of neighbor points. If the count of distinct label points among its surroundings exceeds a predefined threshold tau, we identify the central point as a boundary point. We finally generate a pseudo-binary edge map E, where points on the edge are 1 and internal points are 0 for the entire set of points. With dynamically generated pseudo-edge labels, we aim to enrich regular features to recognize the accurate spatial scope of 3D instances with precise boundaries. Specifically, we introduce an edge prediction module, which predicts a voxel-wise dense edge map to interactively guide the network in capturing edges of various instances. Given a full-resolution feature map F0 from the backbone network, our edge extraction head, which consists of multiple shared MLPs, estimates the probabilities of edges for each voxel. As edge voxels constitute a small portion of the entire voxel set, we formulate weighted binary cross-entropy loss to train the edge extraction head. Then, we propagate the edge queues of prediction as auxiliary information for the backbone network, improving 3D instance understanding with edge-aware features. We train our edge network jointly in an end-to-end manner with low computational costs. Now, I will present the experimental results of our approach. We first compare our proposed method with existing state-of-the-art methods on multiple challenging benchmarks. As reported in Table 1 and 2, ours generally outperforms other methods, achieving the highest score. Also, as reported in Table 3 and 4, our method demonstrates significant advancements on both datasets. These results confirm that our edge queues and smart semantic prior benefits the entire network, leading to high precision in 3D instance segmentation. In this section, we conduct comprehensive ablation experiments to verify the effectiveness of individual modules. In Table 5, we evaluate the variance of our method with and without the semantic network and edge prediction module. The addition of 2 modules improves accuracy across all experiments. Notably, integrating SN and EPM leads to considerable advances, confirming the effectiveness of each module. In Table 6, we conduct various applications of text embeddings to determine the most effective strategy for the functional understanding of complex 3D instances. Applying the semantic knowledge across the entire transformer decoder through the semantic fusion outperforms other applications. Here, we explore the impact of the coefficient value of edge loss on 3D IS accuracy. First, as shown in Figure 5, we empirically find that weight value influences the thickness of edges in a 3D scene. In Table 7, we observe the correlation between the scene scale and the weight value. The optimal value for edge learning is proportional to the scale. Besides, methods using high-resolution feature maps for edge prediction generally perform better than those using low-resolution features maps. In this section, we qualitatively confirm the usefulness of our novel framework. These results demonstrate that our method provides more detailed and robust segmentation results than the baseline method. In conclusion, the main contributions of our work are summarized as follows. First, we propose a novel 3D instance segmentation framework utilizing the rich semantic clues from the language model. Specifically, context details of text embeddings serve as smart semantic priors, effectively enhancing the functional comprehension of complex 3D instances. Second, we introduce the edge prediction module, which guides the entire network to take advantage of edge-aware features. We also utilize the module's output as auxiliary knowledge for learning edge cues, boosting 3D-IS performance. Finally, we analyze the effectiveness of our proposed method on multiple challenging benchmarks, including ScanNet v2, ScanNet 200, S3DIS, and STPLS3D. Extensive experiments on various 3D scenarios validate that our method achieves new state-of-the-art performance on 3D-IS. Thank you very much for your attention.